Hello, everybody. So let's go ahead and get started with today's lecture. So we're going to be doing section 2.7, which is on cylindrical and spherical coordinates. Um, Now, I don't even want to say it because I'll probably jinx it and make it take twice as long. But I feel like this is a relatively simple topic, and we can do it in less than the hour and a half that a lot of these other lectures have been taking. So let's go ahead and talk about it. So we're going to start with cylindrical coordinates because it's going to be the easiest. So let's write that. Cylindrical coordinates. All right. So um, also before we do that, I guess let's move this down and say a little bit. So just like in 2D, right? In two dimensions, in 2D, um, you have the normal rectangular coordinate system, which some people will say rectangular and some people will say Cartesian coordinates using X and Y, right? That's how you normally do it. But you also have polar coordinates, which hopefully you have seen at some point. You also have polar coordinates. And that's where you represent position by r and theta. Okay. And maybe even I'll draw a little picture of that just to remind you, and then we'll move on. Right. So, in two dimensions, right? So you have an X and you have a Y. And then if I just take a point here and I just call that point XY, right? You can represent its position by its X coordinate and its Y coordinate, right? But you could also represent its position by an R and a theta, where if you draw a line like this from the origin out to the point, then you can measure this angle, which we call theta. And of course, the distance here is the R, right? And then so using the R and the theta, you can represent this exact point just like you can in X and Y, right? And yeah, so we're going to do the same sort of thing, but in three dimensions instead of two dimensions this time. And that's all. That's all that we have to do in this entire lecture. Just talk about cylindrical and spherical coordinates. So first one we're going to use is cylindrical. So in this coordinate system, so in rectangular coordinates in space, we've been using X and Y and Z, right? X and Y and Z to represent all positions. Okay. In cylindrical coordinates, we're going to use different variables. So we're going to use R and theta and Z. And so when I say R and theta and Z, then you recognize R and theta from polar coordinates, and actually they're going to mean the exact same thing. So in cylindrical coordinates, we will use R and theta and Z. And so how do we define them? Well, the R and the theta are exactly the same as from polar coordinates. So the R and theta are the same ones from polar coordinates in 2D. And the z is just the z variable from xyz. So it's the regular z from xyz. Okay, now I've got a picture to show you, so let me find it. Photo library. Scroll down. There it is. Boom. Guess we have to put it down here. Okay. So these are the polar coordinates for x, y, and z. So normally for x and y and z, right, you've got, well, we already drew once, x and y, and you have a point, and we have an angle from the positive x-axis up to that ray, and then we have a radius, which is measured that distance there, right? And so if you look at this picture here, you've got this theta right here. That's the same theta that I drew over here. This is the xy plane, and the ground is the xy plane. So x is here, y is here. So that theta is that theta, that r is that r. And then because we're in 3D space, we need some way to represent the height. And so we just use the regular z variable from xyz. We just z. Okay, and that's cylindrical coordinates. So this is just a picture of cylindrical coordinates. Okay, so how are we going to deal with these, right? So you're going to have to be able to convert back and forth between cylindrical and Cartesian. And so there's a set of equations that you'll have to learn. They're actually the same ones that you will have used previously in other classes for polar coordinates if you've done them. If you haven't done polar coordinates, then of course this is not going to be, then this is going to be new, right? So theorem. So this is going to be conversion between cylindrical and Cartesian coordinates. Now, some books use the word rectangular a lot, and some books use the word Cartesian a lot, and it doesn't really matter which one you use. People will know what you mean. All right, so conversion between cylindrical and Cartesian coordinates. So we can say x, y, z, and r theta z are related by these equations. So the first is the way you calculate the x value is that it is r times the cosine of theta. Again, this is straight from the conversions for polar coordinates. The y coordinate is r sine theta, straight from the conversion to polar coordinates, right? Because you got this picture here. Color orange. So like this line right here, in terms of r and x and y, you have r equals, you have y is equal to r sine theta. And then this side here of the triangle is x equals r cosine theta. And then the third side of the triangle is r. So we have those. Then we have, what do we have? Now what's the z? Very complicated. It is just z. Okay. So these get used to go from cylindrical to rectangular. Cylindrical to rectangular. But then there's more because sometimes you have to go the other way around. So if you have to go from rectangular to polar, then you use r squared equals x squared plus y squared. That will let you find the r. And then tangent theta is equal to y over x. That will help you find the theta. And the z is equal to the z again. So use these for rectangular to polar. I keep saying polar when I mean cylindrical because they're the same thing. Okay, so when you're first starting out, you're going to have to convert between, a set of points in one set of coordinate system to the other coordinate system. So let's just pick a couple of questions and then we'll finish out with a little bit of other stuff here for this topic. So here's an example. Convert 5 pi over 6 4. Oh, hold on. Sorry. I copied the wrong question here. I could have used that one, but I'm changing it. 4 2 pi over 3, comma, negative 2. I'm going to plot it. Let me erase this. Plot. And convert to rectangular. Oops. So this must be in cylindrical. Now you might think like, of course it's in cylindrical because it's got a 2 pi over 3 for theta, but you don't actually know that, right? Like this could be x, this could be y, this could be z. So you can't just assume that it's in cylindrical by looking, okay? Those could have been rectangular as well. They could be spherical as well. You don't know. So that somebody does have to tell you what they are, and then they can say convert to rectangular coordinates. So the reason I wanted to plot it first was just to make sure we understand what's going on in 3D space. So let's try to do that. My picture will go off onto the other page. That's fine. Okay, let me erase that actually, what I just drew. Okay, so how do you do this? So we have to think about how to do this. The theta is measuring from the positive x-axis around this direction for theta. So like around counterclockwise is theta, which is also true for here for in 2D space, okay? So you're measuring from the positive x-axis around. So we come down here and say, well, here's the positive x-axis. Oops. Here's the positive x-axis. So we're going around this direction. That's the positive way to go around. What's our theta? So our theta is actually 2 pi over 3. So we're going around this direction, 2 pi over 3. Right? So we have r equals 4. Theta is 2 pi over 3. And the z value is negative 2. So if I'm trying to do this, it's a little bit tricky. So I'm going to extend the x-axis this way. That's the negative x-axis. Now, I see that this angle here is 2 pi over 3. So pi is 180 degrees, right? So from here all the way around this way is pi, and this is 2/3 pi. So it's 2/3 of the way from here to here. So it's hard to get that in exactly the right place, but you can maybe go like that. And that's flat on the ground, and so that distance is 2 pi over 3. Okay, now it kind of looks like it's pointing up in the air, but it's not. All of that is in the XY plane, right? I'm trying to draw it halfway in between the Y and the X axis here. Not halfway, but partway. Okay. Now then you've got your R, which is 4. So R equals 4 means a distance of 4 in this direction. So if I, maybe 4 is like here, right? But then, right, a radius of 4 is actually like that or something in the XY plane. Don't need to draw that. But so that's saying that this distance here is 4. Okay. Now, once you find that place where you've got the radius is 4 and the angle is 2 pi over 3, then we can do the z value. The z value is -2. That just means from this spot, you go down 2, however far that is. So you erase some of the extra lines here. So from there, you're going to have to drop it down by -2, and then you have that spot there. It's below the xy plane, and that would be P4 2 pi over 3 -2 in terms of x, y, and z. Sorry, r theta and a z. All right. So plotting is not that bad, really. I mean, you don't really plot very many things that way, but you can plot it just the way you do x, y, z. So we plotted that one. The other thing we were supposed to do is we're going to convert this to rectangular coordinates. So that was like, this is part A, was that, and part B is convert to rectangular. Okay, so I've got my calculator here, and we're going to convert this to rectangular. So we're going cylindrical to rectangular. So we should be using these equations. These are the ones that we want. So I'm just going to copy them, duplicate, bring it down here. These are the ones we want. And let's just fill in the numbers, right? So we got theta is 2 pi over 3. Let's fill it in. We've got r. R is 4. And then we got z is -2. So z is going to be -2. So it's as easy as that. And then we just need to figure out what these are as numbers. I don't really need to rewrite the -2. So you need to know cosine of 2 pi over 3, which use a calculator if you have to, use Wolfram Alpha if you have to. If you know your trig, then you know your trig. Oops. Here. I just want to get my calculator set up to do this properly. Okay. Right. So cosine of 2 pi over 3 is going to be -1/2. So it's a -1/2 times 4. So -2. Then sine of 2 pi over 3 is going to be positive square root 3 over 2. So you get 4 times square root 3 over 2, which is going to be 2 square root 3. And then you have -2. So in cylindrical, it's what we had, 4 comma 2 pi over 3 -2, right? That's the r, theta, and z. And in terms of x, y, z, it's what we just calculated, which is -2 in the x direction, positive 2 square root 3 in the y direction, and then -2 in the z direction. Which, looking at here, we'll see if that makes sense. So this says -2 in the x direction. So that would be like 1, 2, -2. in the x direction. And then in the y direction, it was positive 2 square root 3. So that's like 2 square root 3. And then that kind of intersects right there. And then the z value is negative 2. So that's just, again, straight down from there. And that's how you convert a single set of coordinates from cylindrical to Cartesian. Very easy. Just plug in the numbers and make sure that if it's common angles, like not common, but like even angles, like 30 degrees, 45 degrees, 15 degrees, even stuff like that, stuff that's an exact angle, then make sure that you're using a calculator or Wolfram Alpha or some tool that will evaluate these exactly, right? Like this one was square root 3 over 2. If I don't calculate that exactly, I'm going to get it wrong if the problem told me to calculate it exactly. Okay, so just be advised. Should you be getting a decimal or should you have an exact answer? Okay. So let us try the other way. We'll go from rectangular to polar or cylindrical, which is a little bit harder. Example, convert rectangular 1, negative 3, 5 to cylindrical coordinates. All right. So what's the point? The point is really that, not the point, but what you have to be aware of when you do this, what you have to be aware of when you do this is that this isn't that hard. R squared is x squared plus y squared. For the tangent theta, you're going to have to do an inverse tangent in order to get the right answer. And the z is just the z. So let's copy paste these, duplicate them, bring them down. See how that works. Okay, so there we go. So we're going to, I'm not going to write over them like I did last time. So we're going to fill these out. So we got the r squared is supposed to be x squared plus y squared. So just fill in the numbers. 1 squared plus negative 3 squared. So that's going to be 10, right? Right, 1 plus 9 is 10. But that is r squared. You need r, so you're going to have to take a square root. Okay. So that's the first thing to pay attention to. Now it could be technically plus or minus there, but we take the plus unless you have a reason, not to. Could be plus or minus root 10, but we just take the positive one. Okay, so we have the r. Now to get the theta, we're going to have to use this equation. So tangent theta is going to be y over x. The y value is negative 3. The x value is 1. Okay, so you get tangent theta is negative 3. And the way we're going to deal with that is we're going to have to take an inverse tangent of both sides. So theta is going to be the tangent inverse of negative 3. Again, you should use a calculator that can do this exactly because there's certain values here that are going to give you even angles. Like if this was a negative 2, I think it would give you an even angle. If this was a square root 3, it would give you an even angle, and so on. 3, I don't think will, but still, if use a calculator that could give you an exact answer just in case. So I'm going to hit tangent inverse of minus 3, and it's going to tell me the wrong answer. Hold on. Oh, okay. We gotta be a little bit sneaky here. Okay. So let's see. So what we have to do is really be careful here. So let me draw a set of axes. So if you have X and Y here, right? And now let's look at our values here. You have X equals 1, Y equals -3, right? So 1, -3. 1 in the X, -3 down there. So this is 1, -3. Now, if you're trying to find the angle theta, then you have to measure all the way around like this. Okay. So you actually know that. Let me just erase this, by the way. Um, no, actually, not all of that. I want this. Uh, tangent theta equals -3/1. I want that. Okay. Now, you need to actually consider this 2D plot because what you need to see is that your angle theta here needs to be within in this quadrant, the fourth quadrant. Um, so in order for that to happen, you know that the angle, right, this is 0 degrees, 90 degrees, 180, 270, and then 360, right? So it's in between 270 and 360, okay? Or you could say that it's in between 3 pi over 2 and 2 pi, right? So from the picture, from the plot, um, we see that theta should be between somewhere between 180, no, 270 and 360 degrees, or in radians, 3 pi over 2 to 2 pi. Okay. Now, when you do the calculation, the inverse tangent, right? So when we do the inverse tangent, tan inverse negative, well, actually just the tan inverse theta, you always get an answer between negative pi over 2 and positive pi over 2. Okay. And so what you're going to have to do is you're going to have to interpret that answer to get the real answer. Okay. So when we do this, um, so you get an answer in negative pi over 2 to pi over 2, which is not what we want. We want it to be in between 0 and 2 pi. That's what we want. Okay. So when I go from tangent theta to equals -3/1, and I take the inverse, theta equals tan inverse -3. What I'm going to get for theta is that theta is -1.2490 whatever 5, something like that. Okay. That's not what we want. That is measuring this way. That is -1.249. Okay. So you have to remember how angles work and say, okay, if we want an angle, if we want this angle, but we want it listed in between 0 and 2 pi, you're going to have to measure around this way. So it's going to be 2 pi minus that angle is the one that we want. Um, So to get the one we want, right, in between 0 and 2 pi, we have to do 2 pi minus 1.24905. Okay, so you grab a calculator and I do that. I have 2 times pi minus 1.249045772. And I get that theta is 5.034. Okay. Now, depending on what quadrant you're in, right? You could be in quadrant 1, quadrant 2, quadrant 3, quadrant 4. Basically, what you have to do is after you do this tangent, you get a number. You need to look at that number and just say, well, where is that actually over here? And if it's not what you want, you need to figure out what it should be based on geometry, right? Like this one was down this way, and I say, oh, well, that's all the way to get this one, it would be 2 pi minus that. And if you had an angle over here in this quadrant, and you got a number down here in this quadrant, you would say, oh, okay, well, probably the one I want is going to be 180 degrees from that one. So you just have to know a little bit of trigonometry and actually think about this kind of picture in order to get the right answer here. Just think about what quadrant it's supposed to be in and what quadrant it is in. Okay, so after finding, or actually after performing tan inverse whatever y over x, like look at what quadrant you're in and what quadrant it's supposed to be in based on whether x and y is positive and so on. And then you'll have to take that theta and sometimes, add 180 or like add pi to the answer or something, right? Add or subtract, pi or 2 pi to get the angle in the correct quadrant. And also in 0 to 2 pi. Okay, so that's so that's the thing that you have to do. Okay, so what's left? Oh yeah, what I want to talk about now is we want to think about some surfaces. So in rectangular coordinates, right, x, y, z coordinates, x equals a constant, y equals a constant, z equals a constant are all just planes, right? Just do a couple examples. Right, like if you have x here, you have y here, and you have z here, right? If you wanted to plot like x equals 3, you would go 1, 2, 3. 3 is right here, and you need a plane that goes through there. So it's like just a vertical It's just a vertical plane that happens to intersect right there. It's really hard to draw that so it looks right. Trying to think about what I might be able to do here. Maybe I can do this. Like dotted or something. I don't know. So like the idea is that this is coming out of the plane because right here is where it hit the plane that I drew. Or it'll be a lot easier to see for the other planes if you had to do like x equals or y equals 2, for example. Right? So you have y, z, then 1, 2, right? You have that. And then if you wanted to draw a plane, right, where that actually hits right there. That's what I should draw. I should done dashed lines like that. Makes it look like it hits. Okay, so that would be the plane y equals 2, right? And similarly for z, z is like a vertical plane up here. So that's how like x equals a constant, y equals a constant, and z equals a constant looks. They're just planes in space. Okay, but what are those same sorts of things for cylindrical coordinates? It's different. Okay, so specifically, the way it's different is if you have, what if you have r equals some constant k, right? K is a constant. Well, that was, if you think about it, in the 2D plane, x and y, r equals a constant gives you a circle, right? The radius of a circle is constant here. That would be k. So you get that in a 2D plane, x and y. But we know that if you say r equals k, if you have a circle in the 2D plane and the z value can be anything, you get a cylinder, right? We've talked about that in the previous section, where you're going to get, that's what it looks like in the 2D plane, but in space, right, it's going to be a cylinder. Still the same idea. That's your r equals k, is a radius of that circle. But the z value can be anything. Okay, so that's what happens if r is a constant, you get a cylinder. With center. Well, I don't really care about what with center, but with radius. K. Okay, so that's r equals k. Now, what about the other variables? What is theta equals a constant? Right? And again, you should still think about it in terms of a 2D plot first. So if you have a certain theta, whatever it is, right, like theta equals a constant, then all of this is so a ray. So it's a ray, not a line. A line goes that way forever and that way forever. A ray is like a half line. So it starts at 0, 0 and it goes out. Okay. So what would this look like if the z value was allowed to be anything and we plotted it on a 3D plot? What it would look like is you would have like some kind of ray in the 2D plane, but that would extend up as far as you want it and also down as far as you want it. and you get a plane. Actually, not a whole plane, you get a half a plane, right? Um, so it starts at 0, 0, or starts at 0, 0 on the y-axis and goes out in the direction of whatever that theta is. So it's a half plane. So it's a half plane starting at the line z equals 0, the z-axis is what I should say, starting at the z-axis, right? This is the z-axis. And then it heads off in one particular direction like we drew. Okay, I have a better picture. I have the book's pictures as well, so if my pictures are bad, you can look at the books in a second. All right, last thing, z equals a constant. Well, z is the same as z was before in rectangular coordinates. So actually, z equals a constant is just the normal plane floating up in space. Um, so it's a plane parallel to the xy plane. Okay. So those are the three shapes that you can get for r equals a constant, theta equals a constant, z equals a constant. Let me put in the picture of those somewhere. What? Are you kidding me? Oh, that's really annoying. Okay, there they are. All right, I think it's this. Okay, yeah. So this is what happens if r equals a constant. This is what happens if theta equals a constant, and this is what happens if z equals a constant. This is in cylindrical. I'm just labeling it in case you look later on. All right, and those are cylindrical coordinates. So now what we want to talk about is spherical coordinates. So these are the ones that are going to be new to you, probably. Hopefully you saw polar coordinates at some point in your life. All right, so spherical coordinates use this. So let's see. We use rho, theta, phi. Oops. Rho, theta, phi. So some people use a long I there, and some people say phi. Some people say phi, some people say phi. Don't ask me which is correct. Um, Most English speakers say phi. Um, I'll probably mix them up all the time. But rho, theta, phi. And by the way, handwritten, you usually see it the way I just wrote it. It's usually looks like that. Typed, it often looks like this. Uh, yeah. So looks a little bit different depending on where you see it. Actually, it looks like this in your textbook, so there's that. So maybe I didn't even need to write this, but we use rho, theta, and phi. And then what are they? Rho is going to be the distance from the point. So if this is P, from P to the origin. Okay. Theta is going to be the same theta from cylindrical coordinates. But this time we're not using a z. We're using a phi or a phi. This is going to be the angle formed by the positive z-axis. You're going to need to see a picture for this. The positive z-axis and the line segment OP, where O is the origin and P is the point. Okay, so one thing we can say about this is that we should have theta is going to live in typically 0 to 2 pi. But nothing really forces it to, right? If you had 4 pi, you could go around the circle twice. It's not actually a big deal. So that's usually. And phi is going to be between 0 and pi. And this one actually kind of matters more. I don't know. Maybe I shouldn't say it that way. So let me get the picture so we can see it. I'm going to use their picture rather than draw it at first. Where is it? Gone, of course it is. Yeah, that's useless. Delete. I'm going to steal it from here. There it is. No. Okay. Where is it? Give me the picture there. Okay, there it is. Boom. Okay, this is going, probably you can see, incredibly slow. Very jerky. So I have to close this real quick. Give it a second to settle. Close this. Come on. Close Notability, open Notability, open the notes. There it is. Okay, not fast again. Okay, so let's look at our picture here. So the distance rho is from the origin out to the point. So this is the point. Okay, so we're measuring here. This distance is rho, as they say. Maybe I'll just draw my own rather than scribble all over theirs. Maybe that's better. Okay, so I'm just going to put this point up in space. Okay, let me erase. So you measure this distance rho. Now that's different than what we did for r, because r was measuring just in the xy plane. Rho is measuring a distance in 3D space. So rho measures that. The theta is the same theta as before. So what you have to think about happening is if this point was projected down into the plane, right? Like maybe it's right here. That's its projection in the plane. Then the theta is measuring this. Okay, so that's still from the positive. That's from the positive x-axis measured around counterclockwise, just as before. So from there to there, that's the theta. And then your last variable is phi. You actually measure phi as the angle from here down to this ray. So you have the z-axis here, and you measure this angle. That's the angle phi. Okay. So, I mean, I just drew it myself in case this picture is hard to understand. I don't know. That's spherical coordinates. And the reason you see that these are between, this one's between 0 and 2 pi, that's because theta can be measuring all the way around a circle, right? Here is like 90 degrees, 180, 270, back to 360. So it's all the way around. Whereas phi measures from here. So if you think about it, like straight up is 0, phi equals 0. If you measure down to here, that's 90 degrees. If you keep measuring down here, you get to 180. So straight up is 0, straight down is 180 degrees, and there's no reason to ever go past 180, right? Because everything is either straight up to straight down. And, you know, if it's over here, you say, well, what if I needed to go 90, 180, and then past 180 to get back over here? Well, over here, if you went around over 180, that would just be the same as measuring from here down, and it would be less than 180. So you never need to measure more than 180 degrees for phi, and so we don't. We just go 0 to pi. Okay, so those are kind of the restrictions on those. The conversions between rectangular and spherical and cylindrical are more. There's more conversions, and it's a little bit trickier to do. But it's the same game, right, as before. So let's say conversion. Converting spherical, cylindrical, rectangular. So first of all, maybe we'll derive some of these, but the x is going to be rho sine phi cosine theta. The y is going to be rho sine phi sine theta. The z is going to be rho cosine theta. All of this stuff comes from, I said theta, but that was a phi. All of that comes from regular trigonometry. We can draw some of them maybe after this. And these three you would use from spherical to Cartesian, right? Spherical to rectangular. So use for spherical to rectangular. And you've got three more. I'll do a different color. Rho squared is equal to x squared plus y squared plus z squared. And tangent theta is equal to y over x. And phi is arc cos z over square root x squared plus y squared plus z squared. They probably could have just labeled that as r, z over r, but they didn't. All right, so these are from use for rectangular to spherical. Then we can do two more. R is equal to rho sine theta. No, so rho sine phi, sorry. Theta is theta. Z is rho cosine phi. So you would use these if you're trying to find r theta and z. So these are spherical to cylindrical. By the way, this isn't as complicated as it looks. I'm like writing all of these equations down, but you just use whichever, like, you know what you want to end up with, and you know what you have. So it's not that hard to pick the right set of equations to use. Okay, last one. Last three actually. Rho equals square root. That's not square root. I was looking up at something. R squared plus z squared. Theta is theta. And phi or phi is arc cos z over r squared plus z squared. Okay, and these would be used if you're going from cylindrical to spherical. Okay, so you have a lot of conversions because we just have three different types of coordinates now, and you can convert from any of them to any of them. Now you do get these all just straight from trigonometry. I don't know if I really want to derive all these, but so I won't actually. So I won't. But let's think about what like rho theta or rho theta and phi would be if they were equal to a constant, just like we did for the cylindrical. Um, let's see. Rho equals a constant. Theta equals a constant. And what? Phi. Erase. Phi equals. That looks like a gamma. Let me rewrite this. Okay. Rho or phi equals a constant. Okay. What surfaces do you get? Okay. So rho equals a constant is pretty obvious. Rho is a radius again, being measured from the origin out to a specific point. So if rho is a constant, it would be all of the points that have that same radius. All of the points in 3D space that have a same radius form a sphere, which is why these are called spherical coordinates, by the way. So all points satisfying rho equals a constant form a sphere of radius k. I should put a k here. Okay, so I think that's pretty clear. Right? Like if you have this is like rho equals 3 or something, right? Well, that's rho equals 3, but also, this is rho equals 3. Also down here is rho equals 3. This is rho equals 3. This is rho equals 3, right? And when you're done at the end of the day, those everything of distance 3 from the origin just gives you a sphere. Okay? So that's pretty straightforward. Now, theta equals a constant is the exact same situation as it was from before because it's, we already did it, right? It's the same theta for cylindrical coordinates and spherical coordinates. So since theta in spherical coords is the same, as cylindrical, this is the same too, right? You get a half plane from the z-axis. So your picture looks like, see, I knew I shouldn't have said that this was going to be a short lecture because everything is taking me longer and it's not a short lecture, right? So the idea here is, you could put, theta is somewhere. Why did you do that? Theta is somewhere in the xy plane. I drew it too much. Okay, that's good. A little further. Right, like theta equals a constant could be there, and you get that like this entire array. But of course, you extend that up and down, and you end up with just this plane. Also goes below the axis, like that. So half plane. Okay, so the last thing is, what is phi equals a constant going to be? Phi equals a constant. And so in order to figure this out, you got to think about it a little bit. So you have to think about where phi is, first of all. So look at the picture. Phi measures just from the positive z-axis down to that ray. So like if you had like phi equals 30 degrees, that would mean from here down 30 degrees. But it's not just here 30 degrees. This way 30 degrees is the same thing. And, this way 30 degrees and 30 degrees back, right? From here down, anywhere in a 360 degree circle is still going to give you the same phi equals whatever, right? So what I'm trying to say is this. So like, imagine that you do down this way, right? And by some amount, phi equals k. You get a line like that. But you also get that same one if you come here down this way towards the x axis. That's the same, could be the same phi. But you also get it if you go, back that way by the same amount. And so what happens is you actually get, that's not what I wanted. You actually get this kind of thing going on, a cone. Because everywhere on that cone is the same phi equals constant, right? The angle from, trying to get the pointer, the angle from here down to the cone is the same as the angle from here down to the cone on this side, and the same as the angle from here down to the cone, on the x-axis and back to the back of the cone. So no matter what, it's still going to be the same phi there. Also, you can have a negative. Well, okay, no, I shouldn't say that. I was going to say you could have a negative radius, but we're not going to use a negative rho. Say rho is positive. So you end up with this half cone is what we ended up with. So it turns out you get a half cone. Okay. I mean, that's about it. Let's get the pictures from the book just so we have them. They disappeared again. I'm really, 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 really annoyed with the way this is working. Like I get a picture and then I come back for it and the picture is not there. Even though I'm looking at all of my photos. Oh, well, I'm not going to include it then. These are pretty clear, I think. Oops. So you get a sphere, You get a half plane and you get a half cone. Okay, so let's do some just conversions, and we'll look at a couple of equations too. So let's see. So example, let's convert spherical 8 pi over 3 pi over 6 to both rectangular and cylindrical coordinates. All right, so how would you do that, right? So we know that this is rho, theta, phi. Okay, so what we're going to do is we're going to have to figure out like what are the right conversions. So to convert to rectangular, those are going to be this top group, right? This is for spherical to rectangular. So you go here, duplicate. We're going to use these. So you put in your numbers, and yeah, so you put in your numbers. So you have x is going to be simply rho, which is 8, times the sine of phi, which is sine of pi over 6, times the cosine of theta, which is cosine pi over 3. So you work that out. So it's 8 sine of pi over 6 is a half. Cosine of pi over 3 is also a half. So you have 8 times a half, which is 2. Then you got y. Y is going to be rho sine phi again. Then you have sine theta, which works out to 8 times a half. And I put sine theta, but I meant sine theta. Theta was pi over 3. So then you need sine pi over 3, which is square root 3 over 2. Again, you can use a calculator that can do these exactly. That's fine. So you have 8 over 2 is 2, and then you still have the square root 3. So I think that. And then lastly, for z, you've got rho, which is 8, and then cosine of phi. Phi was pi over 3. So you have 8 times square root 3 over 2, I believe. And you end up with 4 square root 3. So far, well, I'll just write them all at the end. So that's what we have in rectangular coordinates. Rectangular, we have x, y, z equals 2, 2 square root 3, 4 square root 3. All right, so we got that. So we converted to rectangular. And then you have to convert to cylindrical. And technically, you do have choices. You can use the equations here. No. You can use the equations here for spherical to cylindrical, which this is not going to be that hard to do, I don't think. It looks pretty simple. But technically, you could also scroll way up now and use the you could use the ones for rectangular to cylindrical, because we just found it in cylindrical already, or we just found it in rectangular. So now we did spherical to rectangular. So now you could do rectangular to cylindrical if you wanted. I wouldn't though, because remember that the conversion with the tangent theta was annoying. So I would not do that, but technically you could. So I would just use the ones specifically for spherical to cylindrical. So duplicate that, put me down. And let's go. So we have r is supposed to be rho, which is 8, times sine phi, which is, what was sine phi? What was phi? Pi over 6. Wait, is it? Hold on a second. Oh, I screwed this up. This was supposed to be this was supposed to be pi over 6, right? That was a phi there, which was pi over 6. Like for some reason I looked up here and I wrote that pi over 3 there. Um, but the cosine of pi over 6 is square root 3 over 2. So that value was right, but I wrote the wrong number there. Just sorry about that. Okay. So this is r. R is 8 sine phi. Sine pi over 6 is a half. So we get 4. Theta is just theta, thankfully. That's why I would not use the rectangular formulas. I would just use the ones that we're using. So theta is just pi over 3, the same pi over 3. And then z is rho cosine phi. So rho cosine phi, which is 8 times square root 3 over 2, which is 4 square root 3. So in terms of r theta z, we have 4 pi over 3, 4 square root 3. Okay. So, I mean, that was some conversions between something. Okay. So, one thing that you'll have to do sometimes is they'll give you equations in spherical coordinates, and they'll say, well, what kind of surface is this? So, surface examples, I guess. So, what surfaces are these? So what is theta equals pi over 3, right? So this is just like part A. What is theta equals pi over 3? And, we have some pictures of it already of that kind of thing. But remember that theta is the angle in the xy plane. So you have 60 degrees. So like pi over 3 is like right there. And you know that should make a half plane. Or if you don't know it, right, we should be starting to learn it right now. So it's half plane like that. Okay. Now, what if I have something like phi equals 5 pi over 6? What would that be? So again, we have like some stuff written down. So 5 pi over 6 is almost 180 degrees, right? Pi is 180, and this is like 5 over 6 is like 83% or something. So like this is almost 180 degrees. And you measure phi from the positive z-axis down to the angle. So phi, like if you draw this down here for the negative z-axis, phi equals 5 pi over 6 is like here all the way down to like here. That would be phi equals 5 pi over 6. Okay. But we know that this should give us a cone. So it's not just this one angle, right? Because you can think about rotating this like around 180 degrees. So you can take this line and rotate it around 180 degrees. And then what you end up with is, why draw a straight line? What you end up with is this cone, right? half cone. Wait, I'm checking GeoGebra real quick. They have a weird picture. Oops, I just dropped my pen. They have a really weird picture in the book, and I think they just made a mistake. So I'm just gonna double check it here. GeoGebra, we need calculator. Oh wait, I don't know if I can. Okay. Um, I lied. I don't know if I can do this in spherical coordinates, so I'm actually gonna not do that. Um, I think they just have the wrong picture for this cone. They drew it like this. Like they drew their cone like this. Um, but this angle is less than 90 degrees, which is so it's got to be less than pi over 2. But so that theirs is wrong, right? Pretty sure. Okay. So either way, it's a half cone. Um, let's see here. One thing that they could make you do to see why this is true is they can make you write it in Cartesian coordinates. So I'm just going to make a part C to this, and I'm just going to say um, what is the equation phi equals, that's like I drew a gamma again. What is the phi equals 5 pi over 6 in rectangular coordinates? So they can ask you to convert the equation into rectangular coordinates. So how do you do this? So it's not that bad. So what you want to do is you want to say, here's what you would do. One, look at your equations. Look for the equation for spherical and Cartesian that has phi on one side. That's how I would start. Why are we looking for phi by itself? Because this is phi. Okay, so you look at your equations for that. So we come back up here to our list of equations and we look at all of these equations. So we don't want these because we're not going cylindrical and spherical. We're supposed to be going rectangular. Same thing here. We're looking for rectangular. So for rectangular, we're either using these or these. Okay. Now we don't want these because we don't have any phi's or thetas or anything. So I don't know what I'm going to do with this. Okay. That's why we look down here for these equations where we got the phi by itself. So there's the phi by itself. So this is the one that we want. Okay. So we find this. That's the one that's got the phi. Because we have the phi. Okay. And once we have that, then what we're going to do is our equation is that phi is a constant. Is phi equals 5 pi over 6. So simply make that replacement in the equation. So we want to just take this. That's not what I wanted to do. So we want to just take this and replace it with this. So if we do that, we're going to get 5 pi over 6 equals arc cos z over square root x squared plus y squared plus z squared. So technically this is done, but you wouldn't leave it like this. We should simplify it. Take the cosine of both sides. Why would we want to take the cosine of both sides? Because it's arc cos. That's the inverse cosine. So if I take the cosine of both sides, it'll cancel out on the left. So we'll end up with cosine 5 pi over 6 equals just z square root x squared plus y squared plus z squared. Then you can calculate the cosine of 5 pi over 6. So you just do that on the calculator or just by hand. What is the cosine of 5 pi over 6? It is negative square root 3 over 2. So you get this. If I want to try to clear out this square root, we could square both sides. So if you square this side, first of all, the negative is going to go away. And then if you square the, let me just write it actually, hold on. If you square this and you square this, then you square this side, the negative is going to go away. The square root of 3 squared is just going to be 3. The square root of 2 squared is going to be 4. So you end up with 3/4 there. On this side, you square z and you get z squared. You square the square root and it's going to cancel out, and you end up with x squared plus y squared plus z squared. So then you can take this and you can multiply it up to the other side. Like that. You can distribute that 3/4. So you can have 3/4 x squared plus 3, why can't I write 3/4? 3/4 y squared plus 3/4 z squared equals z squared, like that. Then you can move this over by subtract z squared. You get 3/4 x squared plus 3/4 y squared plus 3/4 z squared minus z squared is negative 1/4 z squared equals 0. Something like that. And this, if you look at what we did last time in terms of quadratic surfaces, you would see that we have the signs here are plus, hey, come on, plus, minus. So 2 pluses and a minus, and then this is a 0. And referring to the different types of quadratic surfaces, we see that this matches the form of a cone. Okay, so it's a cone. Now, we only had a half cone when we drew it, right? We only had a half cone when we drew it. And the reason we have the equation of a whole cone here is we kind of cheated, right? Because when we squared both sides, right, the result became positive, which means there's like two solutions, right? Here's what I'm trying to say. Let me re-say that. Like that's one solution, right, to an equation. That's an equation with one solution. If you square both sides, now you have two solutions. X squared equals 1 is an equation with two solutions. So this has one solution. You square it. Now this has two solutions. And because of that, that same thing happened here. So the original equation, this equation was only the bottom part of the cone here, but after you square it, you end up with a new equation, and that equation is the one that had the cone down here, but also up here. Okay, let me see if I can find something interesting to do that's not too hard. Yeah, okay, let's do a couple of these. Okay. Yeah, this wasn't a short lecture. Sorry, I lied. I knew I was lying. Did it anyway. Oops. So let's see. Rewrite in cylindrical. So these are just samples here. So what if I have x squared plus y squared minus 16x equals 0? What would you do? Right? So we just look up the cylindrical to actually rectangular to cylindrical is what we want. So we just look up the rectangular to cylindrical conversions. So we scroll way up here. Here they are. We want these, right? Actually, probably we want these. So it's kind of the opposite of what you think. So actually, we wanted the, this was supposed to be cylindrical to rectangular, right? That's the ones that we're actually using. So we're trying to rewrite this in cylindrical. So you would think we would want rectangular to cylindrical, but we actually want cylindrical to rectangular because we're not just converting a single point, we're converting an equation, and that's a little bit different. What we want is we want to have a substitute for the x. There it is, right? And we want to have a substitute for the y. There it is. And we want to have a substitute for the x, which we already have there. And also, if you want to, you can use the other conversions as well, whichever ones are useful. So like, where is it? Oh, scroll up. It's really far. So these are the most useful, but this is also useful. So, you can use these as well if you think they're going to be useful. So scroll, scroll, scroll. This is slow, sorry. But it's just nice to have all 6 of these as reference when you're solving this problem. Right? So there you go. So there's kind of 2 ways to do this. So kind of the slightly longer way is this. So we're starting with x squared plus y squared minus 16x equals 0, right? And we're just going to use the highlighted conversions. So let's just replace x and y using the conversions. So the x is r cosine theta squared, right? The y is r sine theta squared minus 16x. X is r cosine theta, again, equals 0. So then you can square these two. You get r squared cosine squared theta plus r squared sine squared theta minus 16r cosine theta equals 0. And the reason this is going to take us a little bit longer is because here you have an r squared and an r squared, which you could factor out if you're trying to simplify this. And you have cosine squared theta plus sine squared theta, and then minus 16r cosine theta equals 0. And then what is cosine squared theta plus sine squared theta? You should recognize this identity, right? This is just 1. So you actually just get 1 times r squared. And this is what I would have for my answer. Okay. Now, if you're going to do it the shorter way, you can write x squared plus y squared minus 16r, wait, what? No, 16x equals 0, like that. And this time, so the first one we did, we only used these 3. But if you add these 3 to the mix, then you can just notice that an x squared plus y squared is automatically r squared. So if you use this one here, then it's going to be faster. So you can recognize that this is r squared. And then you can go r squared minus 16x equals 0. And then this one is r cosine theta. So you have r squared minus 16r cosine theta equals 0. And there you go. So, be on the lookout for these kind of things. You have conversions for x and for y, but you also have one extra conversion that does x and y together to r. So you can recognize that when you see it. Okay. Let's see. Now, what would you do with something like this? Let's see, write in Cartesian again. No, yeah, write in rectangular. Okay, here it is. We have r squared cosine 2 theta plus z squared plus 1 equals 0. Okay, so when I see this, here's what I do. So I look at my conversions, right? Look at conversions for, Cartesian and cylindrical. Okay, when I do that, I know how to convert r squared. R squared is easy. It's x squared plus y squared. So I know how to do this, right? Z squared doesn't have to be converted at all. Oops. Z is just z. So z is just z. That's easy. But then the big question is, what are we going to do with this 2 theta? Now, don't just put in what theta is equal to. Okay. So warning, don't just use theta equals, what was it? Like tan inverse y over x? Because then you have to, like, how are you going to simplify that once you put that in for theta? It's going to be no good. Okay. What you want to do instead is actually use trig identities on that cosine 2 theta. Instead, use trig identities on cosine 2 theta to get rid of the 2 theta first. Okay. Um, and your life will be better. So we have to do that. So let's look up our trig identities, right? So we're going to go trig identities. Right? So we want cosine 2 theta. There we go. So we could use any one of these that we want. It doesn't really matter which one we use. So I'm gonna say like, okay, which one could we use here for the cosine 2x? Right? We have cosine squared minus sine squared. We could live with that. 1 minus 2 sine squared x, we could do that. 2 cosine squared x minus 1, we could do that. I don't really see an advantage to any of those. And so since I don't see an advantage to any of those, I'm just going to pick one. So like maybe I'm just going to use the cosine squared minus sine squared. Okay. So I'm just deciding. Maybe this is not the best one. I don't know. Cosine 2 theta equals, what was it? Cosine squared theta minus sine squared theta. Is that what it was? Yeah. So let's try that one. So we'll do that first on these. So we got like, so we have r squared cosine 2 theta plus z squared plus 1 equals 0. So I've got parentheses r squared parentheses cosine 2 theta is going to be cosine squared minus sine squared. Yeah, that's fine. Plus z squared plus 1 equals 0, like that. So I'm using that identity first. So I use the identity first. Then I can distribute this r squared cosine squared theta minus r squared sine squared theta plus z squared plus 1 equals 0. Then I can just rewrite it to make it look more like what I want it to look like. You'll see why momentarily. R squared cosine squared is actually r cosine theta squared. The next one is r sine theta quantity squared. And then you got a z squared, and then you got a 1, and then you have equals 0. So we do all the simplifying first, and then now use your conversions. And, there's nothing really that makes this easier except just practicing so you know what works badly and what doesn't. But this is going to work pretty well because now what you can do is you can compare this to your conversions, which we got somewhere. Where are they? We just want these. Right? Like shrink this. I don't know how. Okay, just move it down here. So now we can use these conversions. So what you're going to get is that you've got this r cosine theta, but r cosine theta is just x. So really this is just x squared minus r sine theta squared, but r sine theta is y. So that's y squared. And then you've got z squared, but we don't have to convert z. Z is just z. So this is what you get. And then if you wanted to identify this surface, you would have to think about what kind of surface it is. So how do we do this? Let's also identify the surface. So let's identify the surface type as well. Well, if we're trying to identify the surface type, I know that if there's a constant, I should put it on the other side. So I have x squared minus y squared plus z squared equals -1. And then I know that you're not supposed to have a -1 over here. You're supposed to have a +1. So I should multiply everything by -1. And I'm going to get -x squared, +y squared, -z squared equals +1. And then so I look at this and I'm noticing they're all second degree. I know that there's a 1 on the right side. That means it's not a cone, right? Remember, it was a 0 if it's a cone. 1 on the right side. And then I've got 2 negative and 1 positive, right? X and Z are negative. And all of this information together tells me that this is a hyperboloid of 2 sheets, right? Remember, like 2 pluses and a minus was a hyperboloid of 1 sheet. 2 minuses and a plus is a hyperboloid of 2 sheets. So there we go. So I think that's enough for now. I mean, you really do have to practice some of this stuff yourself just to get better at it. But you're just going to basically be starting with equations in terms of one variable and then trying to make substitutions and turn it into the other variables. And that's all you're trying to do. Okay, so I think that's it for now. So I will talk to you guys later. Good luck on the homework. Come to office hours if you have questions. And that's it for now.